Welcome to part 2 of the AudioQuest series. Previously, we examined the circuitry and determined that the theoretical gain was higher than what we were measuring. In this episode, we're going to repeat the same gain measurements, we're going to perform the same analysis, and expose a problem with that analysis, and then we're going to see what we can do about fixing it. I hope you all enjoy. So this might be a bit tricky for you to see, but I have the microphone pointing downwards at my phone, which is here. And what that's going to do is play the file that I produced in MATLAB. Now, in order to reduce mechanical errors in the microphone's position, I've actually taken the Tritron and put it on this extension cable. So I have the microphone, one cable, Tritron, one cable, and then the interface. I'm going to try my best to change it over without doing any disruptions. This clip is 100 seconds long, which is 1 minute 40, and I find some of these frequencies quite painful, so the old noise cancelling headphones certainly help. Without further ado, let's begin the test. The first test is now complete. I'm going to carefully remove the Tritron preamplifier and repeat the test again without touching the gain control on the interface. These two are now directly connected without the amplifier. Okay, the test has now been completed. Let's go over to Tenacity and examine the results. These are the parameters that I settled on for this test. So I used a 44.1 kHz sampling frequency, which is quite standard. The other one is 48 kHz that people use. This is a 100-second clip going to 20 kHz, and we're using 100 steps, which means that the smallest frequency we'll get is actually 200 Hz. And that's just being exported to this file called sweep.wav. So this gives us a very nice kind of comb-like frequency response. If I zoom in, we can see this spreading behavior, but we're not seeing too much overlap. And this step function looks almost continuous, but you can make out the steps there. If I zoom in over here, eventually we'll be able to make out the nice clean sinusoid. So you can see there's some sampling artifacts starting to pick up. This is quite expected because we're approaching the Nyquist criterion. However, we are still within the Nyquist boundary, so we should be able to accurately sample these frequencies. So this is the data that we just captured. You can see it's pretty much what we expect, with the exception of some spikes here, kind of transient spikes as the frequency is changing. You can see the same outline that we actually saw in the continuous frequency sweep, which is pretty promising. Without further ado, let's analyze this data. Okay, so this is the first round of measurement where I did just these two, and we got this nice original game plot with a bit of noise. And this is today's random measurements. Okay, so this hasn't been as straightforward as I planned. Now, we can't really see that much in Excel, so I've gone to MATLAB. I've written some code. This takes in the file. There's some kind of basic operations to give us some convenient variables, like this is the length of samples, or the number of samples essentially, and it uses the FFT algorithm, which is a fast Fourier transform if you don't know. Now this lowercase y refers to the time domain data, uppercase y refers to frequency domain data, and we're doing a few things like that, and then we're just going to plot this data as a line graph. So this is what we've got. If we zoom in, we can see these peaks. They look pretty good. And you can see that this kind of spreading behavior is occurring, but there's sufficient distance between the peaks that we're not getting overlap. However, let's examine a specific point. So this little bit of code is just going to automatically move the graph so it actually zooms in on the axes. So once again, you can see this sort of perfect sync function, and clearly this is the 1000 Hertz excitation, right? However, if you look at that peak, that isn't actually on 1000 Hertz, and if you look at this peak, it's quite visibly off. Now that's a problem if we're going to subtract these two data sets to try and actually determine the gain. We also have all this side data, but that shouldn't really do too much to the result, because it's a small amount minus a small amount, so it should still be pretty small, whereas this is a big amount minus this kind of amount, so we should be able to see that as measurable gain. I've zoomed in to 1 kilohertz just to show you that this is not a simple consistent frequency shift, because then we could just shift the data up and on one of them. These are quite a bit off. This peak is pretty spot on, but then this one is quite a bit off, as you can see. If I zoom in on the peak itself, you can see we also have this strange oscillation, and it's quite trivial to smooth this out, but it is another little factor that can screw us up here. I've written another piece of code which was designed to correct this shifting issue. So you can see we're importing the data again, and this time I actually displayed it, so let's run to there. So you can see the these are the input and output signals. This is quite clear, and if you look at the scales, you see that they're different. But we also have these high frequency spikes and some other artifacts which might be causing us problems. We then apply the FFT, and After that, I did a peak finding algorithm using the MATLAB find peaks. This allows you to only detect peaks over a certain threshold, which is an order of magnitude different for the input and output. And it also allows you to do this minimum distance between peaks, and that just means that we don't double count because of high frequency oscillation. Another way to deal with that is actually to filter those oscillations out, but I decided to go for this approach. This is the output that we can use to test if our peak shifting algorithm is correct. So the code has actually gone through and used this delta function that I wrote to basically produce a normalized frequency index. So if it's on 200.2 Hz, it goes to 200 Hz based on the index difference between the previous peaks. And that's powered by the round function, basically. So we're working out what the delta is, and then we're actually rounding it. And I use points 2 and 3 because sometimes you have an issue with the first point. And you can see that's being converted back to the index delta, which is generating this. So if we take 2 kHz, for example, you can see that this one, which is 2000 point something Hertz, has gone to 2000 Hertz. Just verifying that on the other one. You can see this is exactly 2 kHz. Whereas these ones are some other random value. So theoretically, if we subtract these two waveforms, this value and this value will be aligned. We're then constructing a new vector for the frequency axis. I just called it x new because I based it on some normal interpolation system. I'm using the linear interpolation here, but which is essentially joining the dots, but this really doesn't matter. So if I look at this one, you can see that the continuous lines are the input data, and then we have these circles that are the interpolation. You can see this is pretty good. This is joining the dots accurately. All of that was in the raw voltage value, so I'm using 20 log 10 to go to dB. And then we're subtracting the dB values to get the gain. Theoretically, you can divide to get the linear value, but the dB gain is more useful, so I'm just going to let that play out. And oh dear, we have this mess again. Now, why isn't this working? Well, if we look over here, these are our, I forgot to label these axes, but this is just the index, and these are the amplitude values. You can see that they're kind of aligned, but not quite. It seems like this peak should go over here, and these two valleys are in the right place. It's not really clear what is the issue with this. So I was really focused on the frequency domain and trying to correct things there, but let's actually go all the way back to the first figure and look at the time domain. So you can see the waveforms here. Now immediately we can see these spikes are occurring when the frequency shifts, and there's also some amplitude weirdness that you can see that's rising there and that's rising there, where it should be a perfectly consistent amplitude. If I just zoom in, we can see that there is actually a settling time. So this, if you imagine the envelope of the signal, it's kind of going like this, and the sort of true value is the steady state settled value, which is kind of over here, but then we also have this part of the measurement to contend with. You can see in some cases this is much worse than others. Now, some of this will become high frequency noise in the FFT and just kind of go way over there where we don't really care about it. But there's also some low frequency components here, which is actually lower than the measured frequency. So that might be screwing up the previous measurements over there. I need to do some time domain filtering of this data to kind of pre-process it and get rid of any weirdness that might be affecting us there. But you can see the time steps are actually long enough that it does go to steady state. I wrote this piece of code to try and fix the transient issues. So we're importing the samples as before, then we're taking the envelope, which is like the maximum part of the signal. I'm then using some filtering. I'm then using this one to discretize it. You can all laugh at my spelling in the comments. After that, I'm basically resampling it. Now there's a problem because the audio files might be different lengths, and they are. So what you can do is examine their lengths and choose the minimum one, which we'll use for this sample. This section is basically, we are taking a sample of the envelope and just maintaining it for a long period of time. And what that will do is just make sure that we have this kind of periodicity to it instead of having it change kind of randomly. We're then going through, so this might look a little strange. What we're doing here is actually going from 1 to 1 plus the sample period to 2 times the sample period plus 1, and we're going all the way to the end, but we're stopping short by 1 sample period. And this is kind of the main loop. We have a secondary loop down here where we're going through the sample period, so we in fact do go through each point, and we do get to the end. And what we do is just extract a little section, and we find what the maximum frequency is using this find peaks function. And this gives us this term, this dominant frequency. We then loop through and actually reconstruct the system. This is what this II plus JJ is doing. So we're going through every point, and we're doing 2 pi ft, accounting for the sample period here. And this just makes a perfect reconstruction of the frequency. And what that looks like is this. So you can see that there are no longer those strange transient spikes, and these are all kind of moving in discrete steps, which is what we had at the beginning, but in a more sort of idealized form. This is a reconstructed wave. You can see there that it is just the sinusoids, and they change amplitude and frequency, matching this smoothed envelope function, smoothed and discretized. We're doing the same peak alignment as before. You can see we're missing some peaks down there, so after 15 kilohertz, it's a bit questionable because the algorithm is breaking. I then applied some smoothing, and that gets us this kind of response. Now it does look a lot better. There aren't so many jagged edges, but it's still imperfect. And obviously this part that's just static is caused by the sampling error, and the gain is still terrible. You can still read that it's around 15.75 dB over here. Interestingly, it seems to peak at 18, but I wouldn't trust this analysis. This data is still kind of faulty. Oh, this axis is wrong, it should be dB. we've reached the end of the video and I don't have my perfect clean gain graph. Some of you who had the immense patience to stick around, thank you by the way, you will probably be disappointed by this. However, I'm not disappointed, and I'll tell you why. I didn't know if my sort of crazy ideas of how to restore this waveform would work. Just to see this algorithm come alive and to see my idea about restoring it come into fruition is amazing. The peak alignment algorithm was very successful. You can see we had problems with the low signal, but nevertheless I'm very happy. This peak alignment actually has restored them. You can see there's some delay from the filtering, but nevertheless I'm very happy that it worked at all. We can see we have around 15.75 dB in this flat section here. Interestingly, it peaks 18, so I wonder if the true response is something like that, and then it dips off. Because of this sampling issue, you can't really trust this sort of high result. I'm not sure what's going on there. You can see it in the data as well. You can also see the data kind of going dead over here. Now, it is unfortunate that we didn't get the perfect result that we wanted, but at the end of the day, I am a scientist and I'm not trying to engineer perfect results. I'm trying to measure the world as it is. Now, mathematical analysis and statistical analysis are really not my area. Neither is signal processing. So I would love to get the feedback of others in the comment section below. Maybe some of the things that I did were very kind of obvious, and maybe they even have pre-existing names and things that I could have just plugged in, but I didn't know about that. I am a trained engineer. I do have a degree in electrical and electronic engineering, which included some MATLAB training, but the kind of detailed maths behind signal analysis are still a bit alien to me. So I would appreciate any help I can get. Now, I will do a follow-up video doing a detailed breakdown of the Euphoria audio interface. I've already started the reverse engineering, and I've been doing little bits of that, tracing out that circuit on my free weekends. I'll also be doing a follow-up video explaining the chunk of code that I use to generate the stepped sine frequency, and explaining the kind of overlap problem that we get in the frequency domain. So thank you all very much for watching. If you would like to stick around, I will produce more of these videos. As I said, I do research full time, so I don't really have a lot of spare time and energy to put into this. If you would like to keep seeing these videos, you could always encourage me by hitting the like and subscribe buttons. Thank you all very much for watching, and I'll see you next time.